Hey everybody. So there's a lot of research papers that came out this last week. I'm still catching up on them overall. A lot of them, every single one I've gone over so far has been released by major companies, right? And then so this one is called Internalizing Self-Consistency in Large Language Models, Multi-Agent Consensus Alignment, put out by Meta AI in this instance, as well as Columbia University. And then this was released on September 18th. I'll give a general kind of overview of this paper, and then I'll give you I'll dive into a more simplistic, more plain language overview of the paper overall. So I think this just a little bit down here on page 4 or so. This diagram is the best place to explain and look at exactly what is going on within here. So the architecture and what is going on is very simple at its core. And then I had a lot of thoughts when I first thought about it and went through it, right? So essentially what it is they take a base LLM model and then they clone the model. And so let's say 4 or 5 times. And then so those create different agents. And then they ask those different agents the same question, and then that question samples the probability distribution individually of each one of the individual agents, and then they essentially add, and then they have this majority vote DPO that they have that essentially the models come to a consensus based off of say 4 agents, right? So the probability distribution 1, 2, 3, 4. They ask the question, 1, 2, 3, 4 gives their answer. That gets thrown into the probability distribution for the majority vote DPO, and then the majority of that probability distribution then becomes essentially fed back into the models, and then they're trained on that via DPO, right? So it's reinforcement learning utilizing multitudes of agents during the training process, right? This exact process is done currently right now at inference at test time, test time. But the big innovation within this is that they're doing it during the training process itself. And within the training process itself, my first thought within that was why is this not just distillation with extra steps? Because that's what it seemed like to me at first, right? But the reason why this isn't just distillation with extra steps is because of the 2 algorithms that they put within this, and on top of this, how they get to this, right? And this majority and minority is because of this majority vote DPO and majority vote KTO algorithms that they do. And then so these are it's not so. If you were just to distill, say you were to create 4 clones, right? Agent 1, 2, 3, 4, and then you just distilled those, you're going to get just the distillation, basically the same probability distillation by just distilling the overall probability distillation. Right? The model's not actually learning off of anything. It's going to just be, you're just going to be increasing its confidence within that. Whereas when you're splitting it into 4 different agents, you're literally sampling the probability distribution 4 different times. And then so that literal probability sampling of the whole distribution, probability distribution is what you want, right? And that's what you plug into these equations here. And then that's how these algorithms, how they build out these algorithms overall. So it's a super cool framework in that instance, right? The models just debate themselves, and then they're able to improve. It's the plain English explanation of that, right? And then with that said, I'll dive into the more plain English summary of the research paper overall, right? And then so the problem is that large language models, or LLMs like ChatGPT or Claude, are very good at generating text, but they have a common flaw. They can contradict themselves. If you ask the same math or reasoning question multiple times, you might get different answers. So current fixes usually work only at inference time, again, when the model is giving you an answer. So, for example, you can sample multiple answers and pick the majority vote. That helps, but it doesn't actually teach the model to reason more consistently. It just patches out the output. So when you're doing this at inference time, again, you can fix you're taking that what I talked about up front, right? That essentially the same internal probability distribution rather than multitudes of probability distributions, and then you're not actually passing that back through the model, right? Like that model doesn't actually, you don't get the back propagation of that. The model doesn't actually learn from it, from that output. So researchers wanted to go deeper than that. Can we train the model itself to be more internally consistent instead of relying on Band-Aid fixes? So their core idea that they came up with is this MACA, multi-agent consensus alignment. Imagine you copy the same model 3 times and have those copies debate each other about a problem. So each model starts with an answer. They share their reasoning with each other, argue, and then update their answers based off of that. And then eventually they hopefully reach a majority consensus. So the key trick within this, though, is that the system doesn't just care about the final answer. It uses the paths of reasoning that led to consensus as training signals. The model then learns to prefer reasoning patterns that lead to stable group agreement and to avoid those that lead to confusion or disagreement. This is called multi-agent consensus alignment, which is their framework. It's like training the model to be its own debate coach, reinforcing good debates that lead to consistent answers over time. And then so within this, the big thing that people always want to debate within that is what exactly is reasoning within these models? Do they reason, et cetera, overall? So I'll pause there and then I'll talk about that for a second within this, right? So you notice these are different benchmarks for the different models that they're testing this on. And you can see there's, so this one's called math, this one's called GSM-8K, which is also math, and then this one's called math QA, right? So it's testing the model on math. And then so in this instance, mathematical reasoning, right? Does it increase mathematical reasoning? And then the reason why these 3 tests are used for reasoning within the models and for testing reasoning is because it's so I can feed the model a bunch of mathematics, right? And just a whole bunch of problem sets, solutions, etc. And then so if the model just memorizes those and then I give it something outside of that distribution, of the problem set that I gave it, it won't be able to do anything with that, right? Because it would be outside of that distribution. But if the model actually internalizes something within that, there's a reasoning that is going on within that, it has to utilize some sort of reason, internal reasoning process to be able to solve these problems overall and increase its scores on this. And then so that's the logic behind that. What exactly is that reasoning? How do you want to define it? Overall, etc. That's more up to debate, right? But so in terms of what is what we can actually benchmark, prove, and then go over, we utilize math, and then if the model increases its scores on math outside of the probability distribution of these sets, then it essentially it is better at math and reasoning overall. It's the way that kind of works out. So why this matters. This is important because it shifts alignment away from only human supervision, telling the models what humans like, toward self-alignment, teaching the model to value consistency within itself. It's closer to how humans think. Our brains resolve conflicts by comparing competing thoughts and leaning towards stable, coherent ones. I many moons ago was a debater overall, right? And then so I understand a lot of this framework and why it's helpful overall and can strengthen these pathways in unique ways just from that aspect of it and that kind of experience with it overall, right? Which is another reason why this paper drew me initially. And then so how they tested it, they ran MACA on several reasoning heavy data sets, the math ones, everything that I went over, right? And then so models were trained with MACA post-training methods, variance or reinforcement learning, and preference optimization. So they're just so this is a reinforcement learning method. If I haven't explained explicitly spelled that out at this point, and then so it was just trained on that overall. And then so results. So it's basically the big one in GSM-8K is the big one that I look at. It's math word problems, right? 28% improvement on there. 24% improvement on the math data set. And then the multi-agents debates on the math QA got a 42% improvement, right? So generalization, even when only trained on math debates, models improved on unrelated tasks like common sense reasoning by plus 11.6% and science questions by 16.3%, which is another reason why we use these benchmarks within this, right? Because they're the ones that consistent. So if a model improves its mathematical reasoning, it also improves its common sense reasoning scores, science reasoning. I have a paper I wrote like 2-3 years ago on this. It improves like its humor reasoning, everything across the board that you could think of, right? Which is like just why it just happened. We just break it down into this. And then so in simple terms, teaching models to agree with themselves makes them better at reasoning in general. So a few examples. Before training, three model copies debated a gas mileage problem. 2 copies made the same mistake, overruled the correct one, and the group chose the wrong answer. After their training, all 3 used proper reasoning, reached the right conclusion, and agreed unanimously. So the model not only became more consistent, but also learned to collaborate better with itself. Key takeaways. 1 is self-consistency is critical. A reliable reasoning model should give the same correct answer no matter which reasoning path that you take. 2, debate improves training. Using debates between model clones gives richer training data than just majority voting. 3, internal alignment matters. Models shouldn't just align to human feedback, but also to their own internal standards of consistency. 4, general benefits. Training for self-consistency in one domain, math, improves reasoning in other domains, again, science, common sense, etc. And limitations. The method requires the base model to already be somewhat competent. If it's too weak, the debates won't generate meaningful consensus. So like with here, that's like scaling accuracy, right? Just depending on model size, like overall. And then so why this is exciting for essentially the general reader. This research shows that AI can teach itself to think better without needing constant human correction. Instead of being forced to align with what humans tell it, the AI learns to value stability and agreement with its own reasoning processes. It's a step towards more reliable AI systems that don't just sound smart, but also stick to their reasoning and avoid contradictions. And then that's kind of like the bottom line big impact and aspect within this, right? And I think that goes under touch, and I want to highlight on that within this. So what this does overall is it removes more of the human elements from the training process, right? Like a lot of people, I think they have it still within their head, like the majority way that these models are trained and learned is that they're just fed a bunch of data. This data has to be labeled, etc., and then that's how the models are learning. Right? That's called supervised fine tuning. And then so, like ChatGPT 4 as a good example was like I don't know this. They never released. We'll say probably like 70 to 60%. Supervised training or supervised fine tuning, so SFT, and then the majority rest of that was unsupervised learning, which is essentially that same process but without labels, right? And then same thing with like Bard, Google Bard, like all the models out at that time. That's 100% how they were trained. And then you have reinforcement learning step into this process specifically for LLM models, right? Like reinforcement learning is not a new concept like whatsoever, right? Like reinforcement learning has been around since the 1990s. Like all of these things have been around since the 1990s, right? Like a lot of smart people thought about these things for like 40 years, right? The only advantage and the difference today between what we can produce today and what those smart people thought about and theorized about is that they didn't have access to GPUs, like and GPUs and the amount of like compute power that we have today. Like so, I mean, your iPhone absolutely obliterates a 1950s to 1970s supercomputer, like flat out, right? So that's like your iPhone does, and then that's just like an offshoot to you, like, and then so that's kind of just like understanding the progression within these things. Like it's been a long progression within these things, and these things are not like generally like holistically new concepts overall, right? It's just all kind of like building off of these same things, and there's a lot of deep research and a deep well of research of understanding the history, trajectory of these things overall, right? Like this, I've utilized that throughout my entire IT career. Like that's like what has set me apart differently overall throughout my IT career. Flat out is like recognizing that, right? That historical progression, understanding that, looking through it, looking at that from like business processes lenses, like understanding the OKR processes that were like formalized by Intel overall, and then like that deeply understanding kind of that like deep process, like how the history of that was, like why exactly that made them such a great company while they were like fully adherent to that process overall, right? But they're like just highlighting those things within this. So the advancement within that is, so going back to the general discussion is that you have reinforcement learning as a process that is, again, not new, but then is put in, brought into the LLM model process and framework overall and training. And then so with, I don't know, I'm not going to say like where the exact cutoff was for that because I can't remember exactly. Like it was immediately after like BARD and 4, right? That like you see experiments start going with that. And then within that, it was the first kind of iterations within that were like PPO, where you still had a lot of human involvement within that reinforcement learning process. But then GRPO, DPO, like the methods that they're introducing here, etc. Those all build on a process of removing the human more and more from the actual training process that's occurring within these things, right? Like, and I frame it that, and I want to make it that clear and crystal clear because I think like a lot of people have that misconception still that it's required. The human in the middle is a requirement for these things, but that human in the middle element has been eliminated as a requirement basically for all steps within this process, including the training process, right? Because this is like when you're cloning these models, right? This is the human in the middle. It's just replaced by model clones, and then so. I highlight that overall because it's important to keep that in mind, right? Because there should be and needs to be a human in the middle at some point within this process and within these processes, right? Or else the models, they just deviate and start to deviate from that. Like it's not something that you can just take out of the equation 100%. And then so I'm just like, that's the kind of the like danger line with these types of frameworks when we get more and more into this. And so I just want to highlight that overall within this. But so overall, I think this is awesome research. I think this is a super cool paper that's put out, a super cool framework. It definitely caught my eye, made it super interesting for me. So I'll leave a link to both this research paper as well as the doc that I created here, Internalizing Self-Consistency in Large Language Models, Multi-Agent Consensus Alignment, put out by Meta and Columbia University. If you like this type of content, please like and subscribe.